You guys see this okay?
We just see you.
Oh, you just see me? Okay, wrong.
Yeah.
All right, thanks. Wrong screen that I'm sharing. Oh, I didn't click share screen. That's usually helpful if you actually share your screen first. All right, now can you see it? Awesome. All right, so we're going to start today just talking about, you might sometimes call this a scientific method or scientific inquiry. It's sort of about, what exactly is science? How do scientists find out new information? How do they set up experiments? What are the steps to do that? What are the principles of a good experiment? Those are all things that we're going to be talking about today. So here's some scientists. Can anyone know any of these scientists? No? I thought maybe you might know this guy because he's on, what's that show with the guys, they live in that apartment, they're really smart, they're nerds.
Game theory?
Yes, that's right. Stephen Hawking's on Big Bang. He was on Big Bang Theory. This is Stephen Hawking. He's a physicist. Okay, studies physics, and this is, you ever seen this guy, Neil deGrasse Tyson? Okay, another physicist. He does a lot of videos and popular science kind of stuff. This is Jane Goodall. She studied chimps and is a really famous scientist. This is Rosalind Franklin. She is a scientist that helped in determining the structure of the DNA molecule. So those are just some examples of scientists. So when we talk about science and what science is, we can think of it as sort of two ways. You have a textbook, right? I have this big environmental science textbook. Oh, you can't see me, really. And this is a bunch of information, right? This is a bunch of facts that over time scientists have learned through experimentation. So that's one way to think about science. Is like a body of knowledge, a bunch of things we know, and that's not the most exciting science, right? Just a bunch of facts that you read about in a book. But also, science is a way of learning about the world. It's like a process, a set of steps that we use to answer new questions. Okay? We can use science to ask a question, to propose a possible answer, and then to test whether or not that's correct or incorrect. That's what the scientific method or scientific inquiry is all about. Setting up experiments, manipulating variables, testing hypotheses, and coming up with conclusions. And we really use the scientific method all the time. We don't really think about it that way, in terms of sports as an example. I know several of you like sports. If you're experimenting with your form on your foul shots, right, you might make a little adjustment. You might take a bunch of foul shots. You might look at the results and see, okay, did that help? Did that not help? Really what you're doing is you're doing an experiment. You're setting up an experiment. Now, you're not really thinking about it in that way, but that's really what you're doing. Okay? Or if you're playing a musical instrument, okay, and you decide to hold your hands in a sort of slightly different position to see if you can more easily reach the keys of the piano or the flute. Well, you're doing an experiment. You're not thinking about it that way, but that's really what you're doing. Or video games. You're playing video games. You try some technique in your video games. You experiment with it, and you look at the results. You collect your data, and you say, okay, was this successful or not successful? So really, we use the scientific method all the time. We just don't talk about it in this way where we have these sets of steps. So how do we do this? How do scientists actually figure new information out? So we have this sort of diagram that shows kind of a flow of what scientists might do. Now that scientists can do their work in lots of different ways, there's not like a set, do this, then we do this, then we do this. Sort of a more flexible process than that, but this is one idea about the scientific method. So we start with asking questions, right? We want to know something. And that's why we do an experiment, because we're asking a question about the natural world, right? About the world around us. That's what science explores. And when we ask a question, we then typically will come up with a prediction. Well, what do I think? That's called the hypothesis. If I asked you all to define hypothesis, you might say, well, it's an educated guess. That's kind of the definition you learn in elementary school, and that sticks with people a lot. But it's really a prediction. Before you actually perform your experiment, you make a prediction. Like if I go back to my foul shot experiment, if I hold my elbow closer into my body, okay, I think that's going to allow me to make more of my foul shots. I'm making a prediction. That's what I think is going to happen. Now, I don't know for sure if that's correct or not until I actually do the experiment, until I move on to the next steps. Because the next step after you make your prediction is you test it. That's what the experiment is. It's testing this prediction, seeing, okay, was my prediction right? If I hold my elbow here, does that increase, the number of foul shots that I make? That's testing it. And then I collect some data. That's here in step 4. I look at my results, okay? Well, how many out of 100 foul shots did I make? And I compare that to what I thought, my prediction. Was that correct? I predicted I would make more. Did I make more foul shots after making that adjustment? And then that leads me to my conclusion. My conclusion says, okay, my hypothesis was correct, or maybe it was incorrect. Maybe I didn't make any more foul shots in that experiment. Okay? So if your hypothesis is rejected, if your prediction wasn't right, well, maybe you come up with a new prediction. Okay, well, maybe it wasn't my elbow. Okay? Maybe I need to get my hand back farther when I'm doing my foul shots. Okay? And that's going to be a new hypothesis. And again, you go through those steps again. You test it again. Test your hypothesis in an experiment. Compare your results. Make a conclusion. Maybe your hypothesis was supported. Maybe the data you collected supported your hypothesis. And you say, okay, well, yeah, that was right. This data supports the fact that if I keep my elbow in closer to my body when taking foul shots, I'm going to make more of them. So you've learned a piece of information when you did that. You asked a question, came up with your hypothesis, you collected some data, and now you know some more information. That's how science works. By repeating that over and over again, by setting up experiments, that's how we learn new things in science. And so when I look at a big science textbook or something, all of that information in there, the facts and so forth, those facts have been learned through repeated experimentation over a long period of time. And that's how science works. Any questions about those steps or that sort of pattern of scientific method? You probably learned a lot about this in other science classes in the past. All right, so let's get into these a little bit more. So, first off, like we said, scientific inquiry is a way to get new knowledge, a way of acquiring new knowledge of the world. One thing I wanted to mention too, there's also a digital copy of these, and I posted in Google Classroom. So if you ever lose your copy, if you need another copy, it's there in Google Classroom. Okay, so we ask a question. So what kind of questions do we ask in science? Well, we answer questions which we can find out the answer with experiments. Some things are beyond the scope of science, right? I'm not going to do an experiment to say, well, what is my place in the universe? Okay? How should I be a good person? What is better, pizza or pasta? Those aren't scientific questions, okay, that we would answer. Science looks for objective data about the world around us. So some questions we could ask using the scientific process: how does the amount of nitrogen fertilizer affect the height of pea plants? Now let me just grab this telephone real quick. Hello? Hi, Lynette. No, I have it. I didn't send my attendance. No, I'm in my office. I know. I said today I was going to be perfect. I got you. It's right here. It's gonna be there before we're off the phone. All right, bye. Well, was it in this class yesterday? Did I forget to take attendance? And they had to come get me. Yesterday, I forgot. I have 3 classes yesterday, and every single one, I forgot to take attendance. And they had to come down here and they had to tell me. So I got yelled at for not taking attendance. But I did it now. Okay. Some other scientific questions that we can ask. Does increasing the temperature of an enzyme affect its rate of reaction? Do high doses of vitamin C prevent people from getting the common cold? All of those questions, we could set up experiments and we could answer those questions. All right, so that's our first part. We have to ask a question. Well, then we come up with a hypothesis. And a hypothesis is, it's your prediction. It's sort of your answer to these questions you were asking. It's what do you think is going to happen in this experiment? What is the outcome going to be? You always make that before the experiment. There's some important rules about a hypothesis. This is a common question on the Regents exam when you take it in January. They'll ask you to come up with a hypothesis. There's some important things though. Okay? It has to be a statement. Your hypothesis is your prediction. It's never a question. It's always a prediction, a statement of what you think is going to happen in this experiment. So it has to be something you can test. It has to be something you can tell if it's true or false. What we will do lots of times is I'll ask you to set it up in the form of an if-then statement. Like this. If pea plants are given nitrogen fertilizer, then they will grow taller. I'm giving both parts of the experiment. I'm telling you what variable I'm changing, and I'm telling you what results I expect. That's the 2 parts of the if-then. Here's another example. If temperature of salivary amylase, which is an enzyme, is increased to 40 degrees Celsius, then its activity will decrease. I'm giving you the if and the then there. If individuals are given 200% of the RDA of vitamin C, then they'll be less likely to contract a cold. So you set it up as an if-then statement, and that's going to be a good hypothesis. So your hypothesis was what you think is going to happen in this experiment. Well then, once you have your hypothesis, hey, if I go too fast or too slow, guys, or if just let me know. Just speak up and I'll change the pace. It's kind of hard to read if you're still writing things and whatnot. Then once we have our hypothesis, time to set up our experiment. And our experiment is a way to test our hypothesis. A procedure we're going to follow. You know, it's you going to the basketball court and shooting 100 foul shots. Once with your normal form and once with your elbow in a slightly different position. That's the experiment part. And when you're doing an experiment, it's really important you have always 2 different groups. We call them the control group and the experimental group. The control group is the one that's, you sort of can think about it as under normal conditions. You're not changing anything in the control group. Okay? The independent variable, the thing you're testing, is not changed. In my basketball experiment I'm using, it would be, you know, just going to the court and shooting 100 free throws with your normal form that you normally would. Okay, that's the control group. But then in your experimental group, you change something. You're altering something. That thing you're altering we call the independent variable. So you go to the basketball court and you move your elbow slightly. You take 100 free throws. That's your experimental group. Let's look at this example I have on the screen. So here we have some pea plants. Okay? Some are given water and some are given additional fertilizer. The control group is the group that's just getting regular water. Then the experimental group, I've changed something. I've changed this variable, this independent variable, and I gave them extra fertilizer. So I have to have those same groups, those two groups. Imagine if I didn't have the unfertilized group and I just grew these fertilized pea plants, how would I know if the fertilizer was helping them? I wouldn't really have anything to compare them to. So that's why we always need that control group. We need it as a comparison, a group that we can compare our results to. So the control group is treated normally. In the experimental group, we've changed something. And that thing we change is called the independent variable. So as I'm watching you guys here, it looks like most people like to write down like a little bit, like these key points. And then there's a few people just, it's already there for you. You can just focus on the presentation. Whatever you want to do is fine with me. Well, want me to leave that up there another minute? Or we're good? All right. So let's talk about these variables. I've been using that word here and what we've been talking about, these variables. A variable is like something in your experiment that you can measure or change. And there's three categories of these variables. I know you've learned these before. There's something that sometimes people get confused on and they sometimes mix them up. So it's important to try to get them straight. And we'll do lots of practice to help you make sure you understand this. So the independent variable in an experiment, it's the factor, the thing in your experiment that you're changing. It's what you're experimenting with. It's the factor you're altering. And if it's a good experiment, there's only one of these. When we set up an experiment, we really want to just change one thing, see what the effect is. And then if there's other things we want to explore after, we can. But if you change many things, you can't really be sure which is having an effect. So thinking back to the examples that were in our notes, the plants and the fertilizer. Okay, I changed the amount of nitrogen the plants were getting. That's the independent variable. The enzyme, I heated it up to a certain temperature. That was the independent variable. The vitamin C, I gave some people extra vitamin C. That's what I changed. That's what I'm altering in my experiment. That's the independent variable. Let's think to the basketball free throw shooting experiment. What would be the independent variable there? Anybody know what it would be in that experiment? No? Nobody? You just don't want to say? So what do we, when I explained that scenario, what was I changing? Someone, please?
You went through the original thing again?
What was that, Jenna?
You said, what was I changing? I
Yeah.
don't remember what you changed.
Yeah, what did I, so when I went to the basketball court, I changed the position of my elbow, right? I said I'm going to hold it closer to my body. That's what I altered. That's my independent variable in that experiment. All right, I'm going to ask you guys another question here in a minute. Be ready. The dependent variable, that's the data you're collecting. It's the information you're going to use to help you make your conclusion. The data you're collecting. So, in that pea plant experiment, I would measure how tall the pea plants were. That's my dependent variable. The data I'm collecting is going to help me make a conclusion. How much the enzyme is working. That's my dependent variable. In the vitamin C experiment, how many people got a cold versus how many did not. That's the number of people who got a cold. That's my dependent variable. It's sort of the information you take in that's going to help you make your conclusion. All right, let me ask another question. So then in my basketball free throw shooting experiment, what's the dependent variable in that experiment?
The outcome, like what the answer is.
Be specific. Like what is it? If I'm at the basketball court, what data am I going to collect?
Like how far it goes and if it works.
Yeah, and I know if it works by my number of free throws I made. Thanks, Mary. I would just maybe see how many out of 100 free throws did I make. That's the data that would tell me if my change worked. Good. But then there's also this last group of variables, the variables we want to try to hold constant. Because remember, like I said earlier, in a good experiment, you only are changing one independent variable. You're trying not to change anything else. So you can isolate and be specific. That variable had this effect. So usually there's a lot of these variables that we want to try to control. In my pea plant experiment, I gave some fertilizer and others not fertilizer. That was the independent variable. But then there's a bunch of other things I would have to make sure I was keeping the same. The type of pea plant, the type of soil, the amount of light, the temperature. All those things would be examples of these variables held constant. In my enzyme activity, I would keep everything the same except for the temperature, the pH, the amount of the enzymes, etc. In my vitamin C and cold experiment, I'll want to make sure the people in my experiment, both groups are the same age, the same health, the same diet. Then when I look at my results, I can be sure whether or not it's the independent variable that's having an effect. So let's go back to my basketball free throw shooting experiment. So I go to the basketball court, I shoot 100 free throws in my normal form, and I'm looking at what percentage I made. Then I take 100 free throws with my elbow, slightly different. I take 100 free throws, I see the effects there. So in that experiment, what would be some of the variables I would have to hold constant for that experiment?
Time of day.
What was that, John?
Time of day or place.
Yeah, that would be, because maybe I'm just more focused in the morning or afternoon, so I would want to do it both times the same day. Maybe I would want to be in the same exact basketball court. Can anyone think of anything else?
How far back you start.
Mm-hmm. Make sure I'm right at the foul line, each for both of my groups. How about the ball?
Make sure it's the same ball.
Got to be the same ball, right? If it's a slightly different ball, if it's a little bigger, smaller, that's going to affect my experiment. I want to know, how is my form changing? I don't want to do it, like Jenna said, our location. I don't want to do it out at the playground at the high school one time and then do it in the gym the next time. I want everything as much as possible the same. I only want one difference, and that's where my elbow was. So that's what makes a good experiment, that we're controlling all those variables. And once we have our experiment set up, then it's time for us to make our observations. Our observations are just collecting the data and analyzing it. Now, it could be done once. Sometimes you might do it over a period of time. And, some examples for my pea plants. When I'm observing them, I'd be measuring their height, maybe every 3 days for a month. For my enzyme, how much gas is being produced by the enzyme. In my vitamin C experiment, it might be, how many people got a cold during the 30 days when we were doing the experiment. So those observations are collecting your data. In my basketball experiment, it is, counting how many free throws I made out of 100. That's the observations I'm making. And then it's time to make our conclusion. The conclusion say, okay, I did everything. I asked a question. I had my hypothesis. I set up an experiment. I observed the results. Now, what is it actually telling me? That's the conclusion. I analyze my data to see, is my hypothesis supported or was it rejected by the data? We're going to compare our groups. We're going to compare the control group with the experimental group. The group we treated normally with the group we're changing something. Now let me ask you something. Let's go back to my basketball experiment again. Oh, so I go to the basketball court. I just set up a great experiment. Same basketball court, same time, same ball, everything. And I take my free throws with my normal form. And I make, say I'm good, 85 out of 100 free throws. I definitely can make 85 out of 100. Okay. Then I go and I change my form. I'm doing the experimental group. I move my elbow slightly. I take 100 free throws and I make 86 out of 100. Did my experiment, is my hypothesis supported? What would you say about that? Anybody?
Can you ask me again?
So, if I make 85 free throws in the control group and I make 86 free throws in the experimental group, did changing my form work? Did it improve my foul shooting?
Both had 85?
No, 85 and then 86.
Oh, then it improved it.
Does anybody disagree with that? So it is slightly more, right? But the question is, well, is that really important? Like 85 versus 86? Like, is that enough of a difference? Or maybe is that just random, right? Is that just because of random chance? And, there are ways that we can tell whether or not that's an actual important difference using statistics. We're not going to get into it in this class, but we have some math that we can do where we can say, is one basket different actually in difference, or is that just probably chance? So you'll notice here, and I have underlined significant difference. That's a term that we use in statistics. We say, well, is there a significant difference? Sure, there is a difference. One was 85, one was 86, but just one basket is probably not a significant difference in terms of science. So that's an important thing to understand. So conclusions, the pea plants grew an average of 8.3 centimeters taller. Our hypothesis was supported. The enzyme had less activity. Our hypothesis was supported. The people in our two groups that were getting vitamin C got basically the same number of colds. My hypothesis was rejected. So in our conclusion, we are determining whether or not our hypothesis was supported by our data. If it is supported, we can repeat the experiment just to be sure. Scientists will often repeat an experiment several times. We might check our experiment, make sure it's valid or set up correctly. Once scientists do an experiment and have found a conclusion and learned something new, their next step is something called peer review. Who are your peers? What does that word mean, peer?
Like another scientist?
Yeah, peer means like somebody in your group. Somebody, for you guys, your peers would be your other students in, 10th grade. Your peers are people that are like you. So in science, your peers would be scientists that are also studying the same thing. And so scientists then share what they learned with other scientists. They say, hey, I did this experiment. Here's how I did it. Here's the data I collected. And here's what I found. And what other scientists will just say, oh, that's interesting. And maybe they try the same experiment. Okay? Maybe Francis does the free throw shooting experiment. He says, hey, I did this experiment. I got my elbow a little close to my body. I increased my free throw shooting 10%. And he tells his peer, Francesca, who also plays basketball, she says, oh, really? I'm going to go. I'm going to try that experiment. She's going to do the same experiment. Maybe Francesca does it. She says, wow, me too. That's a great tip. And then that information that was gathered in the experiment is spread throughout the community. And in science, other scientists check that work. They can see, okay, I did the same experiment. I found the same results. Maybe they don't find it. Maybe they say, well, I did that experiment. I found something different. And that's how scientists work out those problems with experiments or confirm that what they found is correct by sharing their information with other scientists. Now, sometimes a hypothesis is rejected. The data doesn't support it. Okay? In that case, that's okay. It doesn't mean the scientist made a mistake or they're wrong or it was a bad experiment. It just means that the data didn't support their hypothesis. Often it can lead to a new hypothesis. It can lead to new experiments. And so it's still valuable even if the hypothesis is not accepted. Now, what's important is that our experiments that we design are what we call valid. Sort of, it means set up correctly. And there's some important things to understand about experiments. The larger the number of samples, the better. The more you can repeat something, the better. So, for example, Francis did the basketball experiment himself. Okay, that tells us that's just Francis. Then Francesca does it. Well, now we're getting more people confirming that result. And then the rest of the class does the same experiment. Now, as we get more and more samples, we can be more confident in the results that we found. The more samples we have, the better. If I did that pea plant experiment and I grew the two plants, one fertilized, one not, if I just have 2 plants, well, that's okay, but it's not a good experiment. If I had 100 plants and I gave 50 fertilizer and 50 not fertilizer, that's a much better experiment, a much more valid experiment. You can be more confident that what you found is correct. Also, a valid experiment has just one independent variable and is repeated several times to be sure. Okay, I'm going to ask you guys to think about an experiment. Now, it's similar to the experiment we've been talking about. So I'm going to ask you to do. So do you guys have some questions here on your sheet? I guess they're not showing on my screen. Yeah, you have some questions. So let's just let me give you this experiment. So an experiment's conducted with 30 pea plants. 10 plants are given no fertilizer. 10 plants are given 5 grams of fertilizer. 10 plants are given 15 grams of fertilizer. And after 14 days, the height of the plants is measured. So I want you guys to take a few minutes here and look at the list of questions on your notes. So if you're working on the hard copy, don't look at it for a second. I know it's hard to say because all the answers are in there. So look at the questions and try to think back to what we just talked about and see if you could answer those questions about this example again, this pea plant experiment. See if you could come up with a hypothesis, the independent variable, the dependent variable, and all these other things. If you need to look back in your notes, that's okay, to remind yourself of what those variables mean. But see if you could come up with some answers to these questions, okay? We'll take about 5 minutes to do this.
Where are the questions?
In your notes, Francis, do you see on my screen that looks like this? But you have some questions on yours. It says at the top, an experiment's conducted with 30 plants. You find it? Awesome. Yeah, take about 5 minutes and Do that. Yeah. We're going to take a break after we finish going over this. Just give you guys a heads up. We'll take a break after we go over this, just to give you guys a heads up. And once you guys are finished, just like type in the chat, let me know that you're done. You guys almost there? You guys almost there? All right, I think we're gonna wrap. All right, we're gonna wrap this up and move on here. Just sort of check and see if you were on the right track with some of these. So we have our experiment. We got our 30 pea plants. Okay, 10 no fertilizer, 10 have 5 grams of fertilizer, and 10 have 15 grams of fertilizer. After 14 days, we measure the height of the plants. So what do you think about a hypothesis? What hypothesis is this experiment set up to test?
If the pea plants are given fertilizer, then they will grow taller.
Yeah, that's a great, yeah. So if the pea plants are given fertilizer, then they're going to grow taller. Again, that if-then statement is a great way to set up a hypothesis. If I give them more fertilizer, then they'll grow taller. That's a prediction. Okay. So when I do this, what's the independent variable? Remember, independent, it's the thing I'm changing, the thing I'm altering, the thing I'm testing. So what am I changing about these 3 groups of plants?
The amount of fertilizer?
Yeah, the amount of fertilizer. Some got 0, some got 5 grams, some got 15 grams. That's what I'm changing. That's my independent variable. The dependent variable is the data you collect that you're going to use to make your conclusion. What is it for this experiment?
The difference in size between the plants?
Yeah, that I'm measuring their height. That's what the data I'm collecting, the height of the plants. So what would 2 variables I would want to control and keep the same? So I'm giving them different fertilizer. What things would I keep the same? How about someone that hasn't answered yet? Anybody else want to add? William?
The amount of soil and water.
Yeah, the amount of soil that they have, the type of soil, the amount of water. Can anyone think of something that's not on the list that we don't have here? So amount of soil, amount of water. What else would I want to keep this?
The amount of sunlight?
The amount of sunlight. The temperature would be a good one. So really everything else I would want to keep the same. Okay, so I have 3 groups of pea plants. Which is the control group? Which one of the groups of plants is the control group?
Plants not given fertilizer?
Yeah, the ones that are not getting any fertilizer. Remember, the control group is a group I'm just treating normally. I'm not really altering anything. And so then, obviously, which ones are the experimental groups?
Plants with fertilizer?
Yeah, the other 2. The ones that did get fertilizer. How could I make this a better experiment? Any ideas about how to make this better?
Have multiple plants of the same experiment, because plants oftentimes grow abnormally.
What did you say, Jenna? Have what?
Have multiple plants for each group.
Yeah. In fact, the more plants I can use, the better. Like this was with 10 plants in each group. If I had 20 in each group, that'd be even better. If I did 30 in each group, that would be even better. So the more samples you have in your experiment, the better it's going to be. All right, I'm going to stop this for right now. Okay.